All right. Thank you very much for the kind introduction. So, first of all, thank you very much for giving me the opportunity to speak here. I really enjoy this format. It's great that they're doing this online so that everyone can join. So I hope you'll continue this as long as possible. And you're right, Eric, this is really a combination of my main areas of research: high-dimensional numerics, PDEs showing up, optimal investment, and everything culminates in this project here. It's a joint work with my PhD student, Alex Schütt. And yeah, so the story is basically, well, we have understood for quite a while, at least in theory, how to do optimal investment. So let's say you want to invest in a financial market. Let's make it high dimensional, say S&P 500, where you have more than 500 assets that you can choose from. And you pick your favorite market model. Yeah, let's say you start with Black-Scholes or maybe Heston or something more sophisticated. And you might want to add constraints on your portfolio, since otherwise you will end up with very extreme short positions, very extreme long positions. So just to get more reasonable portfolios, you might want to add constraints on top. And then, as I said, in theory, this is no problem. This has been known how to solve for a very long time. So the constrained optimal portfolio problem, early 90s. I was barely 5 years old when the papers were published on this. And you can choose your favorite method. Yeah? It's a stochastic control problem, so you can use dynamic programming. You can use the maximum principle. There is this nice duality theory, and in principle, these problems are solved. However, if you really want to use these results in practice, then as soon as you go beyond Black-Scholes, well, you run into issues because you don't have closed form solutions anymore. And as far as I can tell, at least, there is very little on actually numerics for situations where we have a complicated market model, so beyond Black-Scholes, and the number of risky assets is large, so beyond 3, 4, 5, I don't know what. And this is what this is about. So we started looking into this, trying to see, with all these new fancy techniques that we have for high-dimensional problems, all of these machine learning methods, what can we do about this? Is there anything? Do they work? Can we solve these high-dimensional optimal portfolio problems? That being said, so here's the plan for this talk. First, the theoretical part. So what's the optimization problem that we're looking at, and how is it solved in theory? Then we'll talk about what we will do numerically, and then some pictures in the end. So quite straightforward. So let's start with the theory. We start with really a standard market model. So Brownian dynamics. Let's make the market complete. So number of risky assets equals number of Brownian motions driving it. And multidimensional model, so D risky assets, and think about D being very large. So for Germany, you would have the DAX, or all the way up to US S&P 500, where, as I said, more than 500 assets are floating around you can choose from. And the setting is you're starting with some initial wealth X today, and then you choose your trading strategy, which here is parameterized in terms of the fraction of wealth you invest in the risky assets. And then once you do that, you write on a self-financing condition, and this determines basically how your wealth is going to evolve in the future. So it's basically proportional. It evolves proportional to your current level of wealth. You gain the interest, you gain excess return of the risky assets over the interest, depending on how much you invested in the risky assets. And there's some volatility term in there as well. Then you fix your utility function for modeling your attitude towards risk. And we'll fix some convex set in RD. And then the aim is very simple: maximize expected utility of your wealth at some fixed point in the future. And the trading constraints are imposed by asking that your risky fractions, your trading strategy, takes values in this closed convex set. That's the problem that we would like to solve. The setting here, the theoretical part, the interest rate R that you see here for your bank account, the returns of the risky assets and the volatilities, they can be quite general, predictable processes, some technical integrability conditions, boundedness conditions you should impose to get a well-defined theory, but this works in quite a general setting, at least the theory, let's say. But now suppose that you actually want to compute an optimal strategy. One of the classical ways would be to think of this as a stochastic control problem. So you write down the Hamilton-Jacobi-Bellman equation, and in the Black-Scholes case, you can see the PDE on this slide over here. That's the thing that you would need to solve. And in the Black-Scholes case, this is still reasonable. Yeah, so this is a PDE where you have a chance of solving it numerically because this has one time variable and one spatial variable for your level of wealth. What is a bit tricky if the number of assets is high is that your risky fractions, so the pi that you have to choose in each state, can be very high dimensional. S&P 500, 500 plus dimensions for this thing. But nevertheless, if you look at the equation, then you already get the feeling that there is some low dimensional structure in there, since the supremum here is essentially determined by constants and the derivatives of the value function, and this has only two variables. So there is a low dimensional structure somewhere in there, at least in the Black-Scholes case. Yeah. So if you want to solve this numerically, you could even try finite difference methods. You have to think a bit about how to take care of the convex constraints, but as I said, in this Black-Scholes setting, there's still a chance that you end up with something reasonable. But as soon as you go beyond Black-Scholes, let's say Heston in a very high dimensional setting, for each risky asset, you then have a stochastic volatility process, which enters as an additional state into the equation. And then you go from one spatial dimension to a very high number, very high dimension in space. And then finite difference methods and so forth, they just don't work anymore. They're inefficient in these high dimensions. So you have to go beyond the classical theory and try to look at, well, some of the more recent developments. And of course, what I have in mind, if you recall the title of my talk, is something machine learning based, deep learning methods, deep solvers for partial differential equations. And while I like these methods, the problem with those is it's very hard to get good error bounds, right? All of the convergence results that you will find in the literature, they have something that they make strong assumptions in terms of your optimization algorithm converges to an optimum, or that the neural network that you're using to approximate a given function is infinitely large. And these are all things which are, well, you need to assume in order to get the theory going. In practice, you won't ever go there. And then it's hard to get really a precise handle on the error that you're doing when you're solving these kind of problems. And that's unfortunate, because while you can possibly solve equations like this, you don't know how close you are to the actual optimum. And that's something that this talk is about. But as I said, for now, just theory. Let's not get ahead of ourselves. So what's the Cvitanic Karatzas idea to solve this problem? They introduce auxiliary financial markets. They're doing so by adding to the bank account on the interest rate R an extra term. And for the risky assets, they're adding two extra terms. And what are these? The delta that you see here, this is formally the support function of the negative of the convex set. The definition you see here. The support function, you can basically think of if you're plugging in a vector u, the support function tells you how far the convex set extends in the negative of the direction given by that vector. That's a geometrical interpretation, not so important for what we're doing here. That's just being added. And why precisely this is being added, you will see in a second on the next slide. So these are these two terms. We're adding this to both the interest rate and to the return of the risky assets. Then we have this additional term here. That's some stochastic process, which is assumed to be valued in the effective domain of this support function. This is because we are plugging it into the support function, and we don't want the values to become plus infinity, so we're restricting it to the effective domain. Yeah, so we are only allowing values of this process nu such that the delta is actually finite valued. And this is a new financial market. It has a different interest rate. It has a different return. But nevertheless, you can write down your wealth equation, and you're doing it in the same way as usual. And compared to the original market, you have two extra terms showing up, those here. Now let's have a closer look at those. So that's the extra term that we have. And you can estimate that. So the first thing that you can do is you can plug in the definition of the support function. Yeah, so that was the supremum over all elements in the convex set, and then minus the scalar product of the elements of the convex set and whatever you plug into the support function. And since we assume our trading strategies to satisfy the constraint, meaning that they are valued in K, we can estimate the supremum by plugging in the value of the strategy. Yeah, so we get a lower bound, and we're estimating the supremum from below by plugging in the value of pi t. And then you see these two terms, they just cancel. In other words, what we've done is we have added something to our wealth, an extra return, which is always non-negative. Yeah, so whenever you introduce an auxiliary market like this, you can do that for any possible process new, you end up with additional return. So these markets are always better than the original market that you started in the sense that, yes, please.
So just to understand this, you understand pi times nu as an inner product, essentially. And that's valued, right?
Yes, yes. So my trading strategies are row vectors, and everything else are column vectors. Yeah, so just shorthand notation.
Okay. Just checking, because I don't want to get lost in the notation. Thank you.
Yeah, you can think of it. This all here works in one dimension, so don't worry about dimensions at this point.
No, I was thinking in multi-D. That's why I was checking. So thank you.
Okay, great. All right. Yeah, so in these auxiliary markets, you always end up with more extra wealth. Yeah, almost surely you get something extra, and this comes from this extra return. Yeah, whenever you have such a process new, and whenever you have a constrained strategy pi. So then you can take expected utility of these terms, yeah, and then it's clear that in the auxiliary market, get an upper bound basically. Yeah, so even if you're optimizing over all constrained policies, and since this works for any auxiliary market, the right-hand side, you can also take the infimum. So the worst possible auxiliary market is still better than the auxiliary market. And then we can make the right-hand side even larger by maximizing over all strategies. So not just the constrained ones, but also the unconstrained ones. This makes it even bigger. And then the deep result of Cvitanic and Karatzas is that, well, under surprisingly mild assumptions, these inequalities that you see here, they're actually equalities. And so meaning the duality gap closes, and the suprema and infima that you see here are attained, meaning there really is a worst auxiliary market. And if you're optimizing in that auxiliary market over unconstrained strategies, that's the same as optimizing in the original market over the constrained policies. And this is how they solve this problem theoretically. They then look at the unconstrained problem, compute an optimal strategy there. Turns out it satisfies the constraints in this worst possible auxiliary market. And then the problem is solved in theory. Let's have a look at how this is done on the in the auxiliary markets. So let's fix one of those. And then what we want to do is optimize expected utility, but overall unconstrained trading strategies. So for simplicity, so that the notation becomes a bit simpler, I am now fixing my utility function, let's say power utility. And then you can solve the unconstrained problem in the auxiliary market by standard techniques. For now, these are standard techniques. One classical way is using martingale kind of arguments, where you first compute the optimal terminal wealth, and then you use that you are in a complete market, so that you know that your optimal terminal wealth can be replicated by a trading strategy. This will be the optimal trading strategy then. And in the case of power utility, you can compute pretty much explicitly what the optimal terminal wealth looks like. So you can also compute what the expected utility of the optimal terminal wealth looks like. It takes this form, utility of initial wealth, and then expectation of some random variable or function of some random variable. And this random variable turns out to be the terminal value of the deflator. So the deflator is the discount factor multiplied by the state price density. So your measure change to the risk neutral measure. Yeah. Not so important what it looks like exactly. You have the market price of risk showing up in there. You have the interest rate showing up in there. But it's just the important part is that we can write it down, and in theory are able to simulate this thing. Right, and then, well, once you have that, you argue that the optimal terminal wealth can be replicated, and then you have your optimal strategy, more or less. For us, the important part is that we know that the maximum overall constraint trading strategies in terms of expected utility is equal to the term that you see on the right-hand side, but minimized over all possible auxiliary markets. And that's the kind of duality that we have. That's the theory, or that's all that we need from the theory. Now let's look how we can turn this into something useful in terms of numerics. And given that result that you see here, it actually almost stares you in the face. So you do two things. When you do numerics, you usually or what you're interested in the end is a trading strategy which gets as close as possible to the optimum expected utility of terminal wealth. So once you have a candidate for your strategy, you have a lower bound. And if you want to know how good it is, you need an upper bound as well. And here the duality then helps you. So you're doing two things. The first thing is that you solve the dual problem. So you try to find the optimal auxiliary market numerically, right? Because if you do that by this duality argument, we know that this gives us an upper bound. So suppose we have an approximation of the optimal auxiliary market. Then we write down the optimal terminal wealth for this thing. This is an upper bound. We do this numerically. And then we go ahead and use any kind of method which gives us an approximation of the optimal constraint trading strategy. And then we know that the expected utility associated with that strategy is a lower bound. And now you see we have a lower bound on the value that we're trying to approach. We have an upper bound on this. And if the lower bound and the upper bound are close, then we know that we've done good. So this gives us a way to evaluate the performance of the trading strategy that we've learned numerically, at least, by Monte Carlo. So this is nothing new, right? This is well understood. This has been used before. This is not our insight. That this is nice for numerics, but this is where we are basing our subsequent considerations upon. And then it's just a question: what kind of numerics do you use for the dual problem and the primal problem? And we've tried several things. So now we are going into a situation where we assume we're in a very high dimensional setting. And then we try our favorite methods, our favorite machine learning methods. I will go through them step by step in just a second and explain them to you. You can do that both on the dual problem and on the original problem. Just come up with your favorite method. As long as it produces an auxiliary market and a trading strategy, then you would be able to evaluate how good they are doing. Yeah? In particular, you can do that numerically. You don't have to show any kind of convergence. Theoretically, whenever using a neural network or whatnot, because you can always evaluate how good or bad you are doing numerically afterwards. What I like in particular about this, something I would like to highlight, is that you're not just able to tell how far the lower bound and the upper bound are apart. You can actually translate that into how much money you are wasting, because both the right-hand side and the left-hand side, they implicitly depend, of course, on the initial wealth that you are starting with. And then you can ask yourself, well, by how much do I have to increase the initial wealth on the left-hand side in order to get the same value as the upper bound? And this can be interpreted as the amount of money that you are wasting by doing numerics, by doing an approximation. How much extra wealth do I need in order to close the gap between lower and upper bound? So this even has a very nice practical interpretation, these upper and lower bounds. All right, so what kind of methods can you use? There are a lot. Here's what we focused on, what we thought might be good ideas. We start with the dual problem. So for the upper bound, we want to compute the worst possible auxiliary market. So in other words, we want to find this process nu, which minimizes this expression over here. And since we already know in this unconstrained problem what the optimal terminal wealth looks like, so basically this has to be minimized over all of these processes nu. They have to satisfy certain integrability conditions. They have to be valued in the effective domain of the support functions and whatnot. But essentially this is it. And then the first thing that we tried is the following. We tried a neural SDE approach. So since nu has to be a stochastic process, we just made the ansatz that it's an Ito diffusion because filtration is Brownian. So there's a good chance that it satisfies a stochastic differential equation looking something like this. So it has some drift term, it has some volatility term, it has some initial value, and we don't know these. So we just parameterize them by functions, here neural networks, and then try to optimize the neural networks in a way so that the right-hand side here is minimized. There's one thing which has to be taken care of, namely that we need that this process here is contained in the effective domain of our support function. You can write down the effective domain, but you have to ensure that if you're running a stochastic process like this, that you're staying inside of this. And we just do so by just reflecting it back. So whenever the process leaves the set k tilde, then we're pushing it back inside by a minimal action, basically. So
quick question.
Normally, yes.
Can you kill the diffusion at the boundary and put the enforce that the drift is pushing inward or at least tangent?
You could.
To avoid the reflection?
Yeah, you could, but this would be a restriction, a further restriction. So there's no reason why this should be optimal, and we don't expect it to be optimal. This is because so the idea is you can think of this as a stochastic control problem as well. And the nu would be the optimal control, basically, that we're looking for. And it is not to be expected that the problem is regular enough so that it is that the local time term doesn't show up. This is because the support function is usually not regular. So you won't have a smooth solution to the HCB equation. There will be some irregularity, and this pops up exactly at the boundary of the set k tilde. That's why reflection was, in our understanding of the problem, the better thing to do because it's more general. In principle, the neural networks could learn to stay away from the boundary if that is better. but reflection is just more general. Yeah, we're allowing this in addition to that.
Okay, this takes me to the other question. Sorry.
Very good. Yeah.
Sorry, because it is a follow-up question exactly because this is very interesting. So you say that you parameterize everything in theta, right? And then you optimize with respect to this theta to get the optimal nu, right?
Yeah.
Okay, so but how do you actually do it? I mean, do you have pathwise gradients? I mean, how does this actually work? Because now you said that you have reflections, right? So, and you said that actually the control may behave in a little bit of an erratic way. So doesn't it affect the way one creates gradients here?
You have to be a bit careful about this. Yeah, that is true. But essentially what you're doing is, or the point is this. So you start with neural network, you compute your path, basically. This allows you to evaluate the right-hand side. And then you would have to push the gradient basically backward through this SDE. And we just use a general SDE solver for these kind of things. So we don't care too much about this. This is kind of the point. As long as it goes through, it doesn't have to be exactly the gradient of the reflected diffusion. It is enough if we're pushing it through the unreflected one and then reflecting it afterwards. The reason why it doesn't matter,
you can make approximations in these steps and the thing is still robust.
Yeah.
Is that so?
Yeah. And
okay.
So it's a very good point. So there are two things which I should mention here. The first thing is the beauty is that we don't have to worry about making this rigorous, as long as we get a good upper bound, which we can check in the end.
I totally found that, and I love it actually. With Christian, we did something on stopped, on optimal stopping actually using this duality, and actually we love it because, like you say, you don't need the convergence theory. You just go and test the bounds, and if they are happy, I mean, if you're happy, then you stop, right? And usually they're pretty good. So I love this approach. That's why I'm asking actually.
Yeah. So we do a lot of dirty tricks. To be honest,
because I expected the dirty tricks at this level. That's why I'm asking, right? I mean, I'm asking.
Yeah.
Thank you. Thank you very much.
You have a keen eye for these kind of things. Yeah, I'm always impressed by these questions, by these observations. It's true. Yeah, and our attitude is really, as long as it works and it runs efficiently and gives good upper bound, then we are happy. Yeah, and that's really the kind of that's the beauty of this approach. That's the neural SDE setting, and we've tried this, and you will see later how well that works in practice. The second thing is really treating the dual problem as a stochastic control problem. So this process nu is now thought of as a control. This is your terminal reward that you get, or terminal cost that you get, and you're minimizing over all your controls. In a Markovian setting, you could write down an HDB equation. So in the Black-Scholes case, after some transformation, this essentially looks like this. This is the HDB equation. If you were able to solve it, then you have an approximation for your control by computing the infimum for each point in the state. Once again, Black-Scholes is a bit boring in the sense that the HDB equation is two-dimensional. So one dimension is time, and the other dimension is a transformation of the deflator. So one-dimensional object, which just runs through the real line. Tricky in higher dimensions is that the control, so the set you're choosing U from, is K tilde. This is D-dimensional, with D being the number of risky assets that you have. Nevertheless, if you're optimizing this thing here, there is a low-dimensional structure in the Black-Scholes setting. If you're going to more advanced models which have additional factors, then this thing becomes higher dimensional and harder to solve. Nevertheless, we have a PDE, and whenever I have a PDE, I feel very happy. This is where I feel comfortable. So we use one of the more recent deep learning methods for PDEs. Here, physics-informed neural networks, or variant of physics-informed neural networks, PINNs. The idea is very simple. you take a neural network, parameterize it in terms of parameter theta, and you're trying to choose theta in a way so that the equation is satisfied if you're plugging in your neural network. What makes HJB equations a bit tricky is that you have this infimum over here, and we tried several things. So the first thing that you can do is actually formally compute the infimum. So taking first order condition and express the optimal u, the minimal u, in terms of the derivatives showing up in the infimum, and then replace these derivatives by your neural network derivatives and whatnot. However, this is pretty unstable, so it doesn't work as well. So what worked better for us was actually replacing also the infimum by a neural network and have it learn the infimum. And then the idea is basically policy improvement or policy iteration. So you're switching back and forth between optimizing the network for W and optimizing the network for the controller, so for U. So in the first step, you're plugging in your control network into the equation. You plug in the network for the solution of the equation. You check how far away from zero you are. You square this thing, check how far you are off. And then you do your gradient update first on the network for the solution. Once you have that, you check how far you are off from the infimum, and you update your neural network for the control. And then you're switching back and forth. So this is pretty similar to what you do in policy iteration, in reinforcement learning algorithms. So you have all kinds of tricks up your sleeve in order to make this even more stable and to improve convergence, if you will. So a few of the tricks that we've tried is actually setting up a very particular structure for the solution, which guarantees that the boundary conditions are always satisfied. That's very straightforward to do, and then you don't have to worry about boundary conditions anymore and just can go ahead and focus on the equation. Then the trick from reinforcement learning, which was really helpful in the numerics, is delayed update of the network. So instead of when you've computed the gradient for the network u theta, you're not plugging in the entire thing, but you're mixing your update with the previous parameter values of this thing. So you're just slowing down, you're regularizing the update for the neural network, and this helped a lot. And that's also a trick that is commonly used in reinforcement learning, delayed updates of the policy network to stabilize the convergence in the.
So is that a damping type of, learning type of update?
Yeah.
Okay. Yeah. So can I ask you a question, because this is also interesting?
Yeah.
You mentioned that if you compute the Hamiltonian directly and write the HGB as it is, right, without the U, it becomes unstable. Did I understand that correctly or not?
Yeah. The reason is that you have basically a fraction showing up involving the first and second order derivatives.
Of course.
And this will be, I think, convex. So the second order derivative might be close to zero, and then the thing blows up, if I have it right. I think the second order derivative shows up in the denominator. And if this is small, then these terms just blow up. And it seems to be more stable if you're parameterizing everything in terms of another neural network, because the fraction itself seems to be much more stable than the individual terms showing up in the fraction. So just numerically more stable.
Okay, interesting. But again, if I understood correctly, you're also using the PINNs essentially. So you sample over the domain and you enforce somehow a discrete L2 penalization of the residual of this over the time and space, right? Is that so?
Yeah.
Any particular choice for the sampling over space-time?
That's my next point. You can improve matters by a clever choice of grid points. So initially we started by just uniform sample on a compact domain.
Yeah.
But you can do better if you, for example, start closer to terminal time, because you're enforcing more of the temporal structure that you have in this problem. Right? This is a stochastic control problem, so it wants to be solved backward in time. If you were to start updating your network at somewhere close to initial time, you will have your gradients propagating through points in time further into the future.
Of course.
And then it's just a
No
lot
good.
less stable.
That's
So you're
not good.
trying to fix good values at terminal time or close to terminal time, and then propagate backward, basically.
Of course,
So by a
and
clever choice of grid points, you can.
Following up on that idea, I mean, you're doing. You didn't say what is the architecture for the network, right? But you said that it was in space and time. So, question: since this problem naturally goes backward, doesn't it make sense, for example, to use some networks that actually are starting from the back, working from some slice of time, then you get that, and then you go to another slice of time and so forth. So mimicking the sort of natural backwards flow of this PD.
Yeah, we get to something similar for the primal problem in just a second. Here, I'm not sure. We could do something here as well. We'll get to that. We haven't tried it for the dual problem because this just worked really well. And we didn't have to improve upon this, but it makes a lot of sense to adhere to the temporal structure or the general structure of the problem. Even in terms of spatial sampling of grid points, I believe very much that it makes sense to sample those points not uniformly, but more according to the state process.
Absolutely. That was a follow-up question, right? I mean, you believe that actually you're going to create a measure here and the state process is not affected by the control. I mean, the one that actually is driving the actual, what is it called? The portfolio, the stocks.
As the deflator. So it enters into the deflator, but the effect, I would say, is not too large. So the structure is pretty similar for if you're varying the control.
Exactly, and
but
that
you could
will tell you
also
how to
resample the grid points if you wanted to.
Yeah, that will help you definitely.
Yeah.
And just
but
one last thing.
resampling the grid points can be less efficient because you have to do the resampling. Yeah, you have to actually do an Euler-Maruyama or something in order to get new grid points. This can slow down the entire algorithm.
Yes, yes.
So there's a trade-off. Yeah.
Yes, and just one last observation that with regards to sampling, right? It is not necessarily the sort of measure of this state that is the best, but it's a combination of the measure of the state and the what is the space that you use for sampling or things like that. I mean, sometimes, for example, if you have a uniform distribution, maybe Chebyshev points do much better than uniform, right? Stuff like that. So that maybe is good to keep it in mind.
Yeah.
And then sometimes you can get to points that are sort of independent a little bit of the measure, but it will work well provided that you know that the measure stays in a certain domain, more or less. That can help you as well. Yeah. Thank you. Also, so sorry for interrupting, but this is very interesting.
No. Yeah, go ahead. Ask as many questions as possible. There's one observation or one thing I am still wondering about is whether one actually wants basically choose the grid points independent of the way that the state evolves, because this would allow you to avoid a possible bias. Right? Because then you have a certain dependence between the grid points because they come from the state process. And if you're just sampling them randomly by some other measure, the update might be more unbiased, but the entire training structure or the entire training, the entire optimization is not 100% understood. And there's actually a large body of literature just trying to figure out how to improve physics-informed neural networks and their convergence, what kind of properties they have. So it's a big area.
Very nice.
But it does make sense to look at the particular structure of the PDE that you're trying to solve. And we saw a considerable improvement when we took all of these things into account. Yeah, and there's even more. I will show you another very clever observation that Alex made which improved the stability significantly, which is actually kind of obvious once you've seen it, but allowed us to crank up the dimension. We'll get to that.
Great, thank you.
Right, so maybe while we're at it, another observation that we made is when the residual is small in your physics-informed neural network, sometimes that still led to a bad performance. So even if the residual is small, this does not necessarily mean for these kind of methods that you got a good approximation. Sometimes we were in a situation where we had a better approximation with a higher loss. Yeah, so this is kind of odd. Don't ask me why, I don't understand it. Has probably to do with all of the things that we just talked about, depending on your grid points and whatnot, structure of the problem. But just looking at the loss is not enough. Yeah, if the residual in the HGB equation is small, this does not guarantee that you computed the function that you wanted to compute pretty well. Yeah, which is a bit odd. All right, let's look for the primal problem. So here we thought, let's be clever about this. So what we want to do now is approximate our candidate optimal constraint strategy. And we already know that we have this dual problem on the other side, and we can compute the optimal terminal wealth there. Yeah, so we have a dual formulation. And the dual formulation implies that, first thing, the optimal terminal wealth can be expressed as a function of the terminal value of the deflator. Yeah, see that here, yeah, up to the utility function, which is in there as well. But it's a function of the deflator at time t. And since we've already done the simulation for the numerics for the dual problem, we have a good approximation of the optimal terminal wealth. So let's use this, because then the only thing that you need is a constrained trading strategy, which gives you exactly this optimal payoff. Yeah, so it's a hedging problem. It's a replication problem. Yeah, so you're now parameterizing your strategy in a way so that it satisfies the constraint. You fix your initial wealth, and you already know what the terminal payoff is that you want to have. And then it's a matter of writing down the wealth equation, the terminal value that you want to attain, and computing both the wealth and the strategy. So that's a backward stochastic differential equation. Yeah, so here's what it looks like. We want the wealth equation to be satisfied. Looks like this. And in the end, we want to end up at the optimal terminal wealth. And the unknowns are the wealth and the trading strategy. And the theory tells us that if we have computed the optimal terminal wealth precisely, then there would be a trading strategy satisfying the constraints such that this here is satisfied and the initial wealth is exactly the one that we started with. And for BSDEs, there are also a lot of deep learning methods, machine learning methods, which work in high dimensions. So you try one of those. Yeah? That's what we thought was a clever idea. And here the ideas are very similar. So you're taking two neural networks to approximate one or two neural networks, depending on the method, to approximate the wealth and the trading strategy. And then you try to minimize the error in the BSDE, typically backward in time. So you start with the terminal condition that you want to get, go one time step backward, and then try to, find essentially a trading strategy and a level of wealth at that point in time so that the residual in the dynamics here are small. Yeah, so this is, to me, this is very similar to what we just talked about in terms of the physics-informed neural networks. But here you have much more of the probabilistic structure given to you because you're working on this BSDE level. And you don't face the problem of optimizing over the control. So it's much more natural to do that back in time because you don't have this extra optimization problem in there as well. And that's it. Yeah, you just apply one of these methods. There are like a lot of different variants of this thing floating around. We just picked one of them. One, this is important, where we parameterize the strategy also as a neural network, so that later we have it in feedback form as a function of the states. For the neural networks, it's possible just by adjusting the final layer to guarantee that it satisfies this convex constraint. Yeah, so you can just encode that into the neural network and don't have to worry about this anymore. So that's the one thing that we tried. The second thing is pretty new. So I was on vacation almost all of August. And when I came back last week, I had the chance to talk to Alex, and he said, he tried something else. And this is the simplest thing that you can come up with is really ad hoc optimization. And this is now essentially what you just suggested, Raoul. You make use of the Bellman principle. So it's stochastic control problem. Bellman principle tells you that if you're starting at time t with wealth x, this is the same as, and you're optimizing expected utility of terminal wealth. This is the same as, we're just optimizing between time t and some other point in time s, somewhere slightly into the future. And then from there, from time s to the end, proceed optimally. And well, this suggests that you should solve the problem back in time, because you already know where you want to end up, the utility of wealth. And you go one step back in time and just compute the optimal strategy on a small time strip. And you do so by parameterizing the strategy again by a neural network. And then you just optimize it on that last time step. Once you have a good approximation there, you go one step back. You've already computed it on the last time interval, and then you're doing it another small time interval beforehand. And like this, you work your way backward in time and get hopefully a good approximation. Yeah, using any kind of gradient descent, stochastic gradient descent algorithm, just propagating the derivatives through the loss that you get. Yeah, so this is, at least as far as I understand, essentially what you had in mind, Raoul, with your question earlier. So this really respects the temporal structure of the problem. All right, not much more. So there are many design decisions that you can do if you're doing this kind of direct optimization. As I said, I haven't had the chance to talk to Alex about some of these. So I still have a few questions. I don't know exactly how he implemented everything in detail. He just showed me last week and showed me the results he got. So this is all fresh, really, really fresh. Just want to give you the gist, because I can't give you more at this point. We haven't had a chance to talk yet. When he presented this to me, I said, okay, but if you're doing it like this is very similar to the physics-informed neural network idea. So you should try this too. This is what we are going next. The primal problem is also a stochastic control problem. So it has an HJB equation, which we could try to solve with PINNs. And since we were pretty successful on the dual side, why not try the primal side as well? Haven't done so yet, but this will be the next step that we are doing. Just mentioning this here for completeness. And I should go a little bit faster through the slides so that I stay in time. So let me show you how well this works, how good or bad this works. We have 4 examples. We started simple, Black-Scholes, 2-dimensional, just as a test bed, to see if any of these methods actually has a chance of working. So you try to look at the simplest problem possible. We do it 2-dimensional because convex constraints in 1 dimension are boring, because any convex set, closed convex set in 1 dimension is a closed interval. And then this doesn't add much structure. It becomes more interesting as soon as you're going to dimension larger than 1. So 2-dimensional Black-Scholes was what we started with, just to see if this actually works, if this makes sense. It worked pretty decent, you will see in a second. So then we looked for something which has a bit more probabilistic structure to it. So we went with a one-dimensional Heston. And then we tried to see how far we can push it. And our goal was to get to the S&P 500, so 500 in three-dimensional Black-Scholes we tried. And once we got this working, we started working on a Heston, 500 three-dimensional Heston. Important, especially in terms of convex constraints. In all of these examples, the assets, and if we have stochastic volatilities, they are allowed to be correlated with everything. Yeah, so it's most complicated setting that you can within these models. And another thing I should highlight is that the entire theory that I showed you is for complete market models, but the Heston model is incomplete. Luckily, this doesn't matter for the following reason. So in a one-dimensional Heston, you have one risky asset and you have one stochastic volatility, and they are driven each by an individual Brownian motion. So if one risky asset, two Brownian motions, that's incomplete. But what you can do is artificial completion of the market. So you're introducing a new asset to the market, driven by the same Brownian motions, and then it becomes complete. And then you are imposing the convex constraint that you are investing zero into the new asset. Then you have a complete market model, but with a convex constraint, and the theory applies basically. Yeah, so we can even handle incomplete models like Heston in this setting. So it's the convex constraints help, so to say. Let's see how well these things went. We'll go through this a little bit quicker. Two-dimensional Black-Scholes. Yeah, so means constant interest rate, constant return vector, constant volatility matrix. The constraint we tried was you are allowed to hold any long position, and short positions should not be larger than the total wealth that you have. So that's the convex set. And the parameters were chosen such that the constraint actually does something. So if you're allowed to do an unconstrained investment in this market, you can compute explicitly what the optimal strategy is, and it's minus 3.9 and minus 0.8. So the minus 3.9 is no longer allowed when you're imposing this constraint, so something has to happen. Yeah, so the convex is, the constraint is actually binding. Methods that we chose was the neural SDE approach for the dual problem and the deep BSDE approach, so the replication approach for the primal problem. And when we ran this, comparing upper and lower bounds, essentially what happens is that you are throwing away less than 0.267% on your initial wealth. Yeah, so for each dollar you invest, you're potentially wasting 0.267 cents. Yeah, so that's almost nothing. Yeah, so we were happy with this because upper and lower bounds, they have to be evaluated numerically using Monte Carlo. So that's pretty much optimal. Yeah, we're not much chance to get much closer to this. But this is only a two-dimensional Black-Scholes market, so might be.
So this waste that you mentioned, essentially we can interpret as a dual gap, right, in the computation. Is that so?
Yeah.
Okay.
So you compute the lower bound, you compute the upper bound, and then you ask yourself, by which factor do I have to multiply the initial wealth of the lower bound in order to get the same value as the upper bound?
Mm-hmm. So it's sort of relative upper bound, a relative duality gap or something like that.
Yeah. We could write down the numbers on the upper and lower bound, but I think this is more intuitive because it tells you how much money you're actually losing by doing the numerical approximation.
Great, thank you.
Yeah, but I could give you more details. I would just have to look up the numbers, but they are pretty close. That's the story. And then you can have a look at different plots. So we know from the theory, for example, that in the auxiliary market, the extra return should be constant. And the neural SDE really does a good job at approximating something which is almost constant. If you look at the scale on the y-axis here, up to the third digit behind the decimal point. They remain within this range. There is still some diffusion, there's still some drift there, but almost negligible. So we learned the auxiliary market pretty well. That's what we got from these plots, basically. Another way that you can compare or look at the results that you get is plotting the terminal wealth, the theoretical terminal wealth in the auxiliary market. So from the dual problem against the terminal wealth that you get from your learned policy. And if the duality gap closes, if they're equal, then everything should be on a straight line, on the diagonal that you see here. And you see this is almost the case. It's barely visible that this is not on a diagonal. So the terminal wealth from the lower bound and the terminal wealth from the upper bound, they're pretty much similar. You can have a closer look at this, but in the interest of time, I will just skip that and instead go ahead with Heston. So here we have one risky asset, one stochastic volatility process, and the constraint is the same in the risky asset as before, and 0 in the artificial asset that we are adding. And I think in the numerics, we just chose the volatility as the extra asset that you could theoretically invest in, but the convex constraint says you're investing 0 in this. Yeah. And once again, neural SDE approach and DBSDE approach. So as in the previous example, and when we ran this, we still got a pretty good duality gap of 0.9%. Yeah, so still less than a cent that you're losing per dollar there on your initial wealth. Here, the dual variable, so the auxiliary market, is no longer constant. That's why this is an interesting example. In the upper plot, you see the adjustment of the return in the risky asset, so the one that you're trading. And in the second one, this is the more interesting one, you see how much you're adjusting the return on the volatility process in the auxiliary market. And here you see the range is a lot bigger. So to go from 2.5 all the way down to -15. And you have a couple of excursions going very, very low. And when we started running these experiments, we had a lot of trouble getting convergence until Alex had a closer look at what actually happens here, why we have these. And the observation, or the big observation that he made is when he plotted this graph. So here he plotted in blue the drift of the volatility process, and in red the extra return on the volatility process in the auxiliary market with a minus in front. Yeah, so you basically see that in the auxiliary market, what the extra return does is cancel the drift of the volatility. And this makes sense because we have the constraint to invest nothing in the volatility process. So if it has 0 return, then you will be, or almost 0 return, that's the area where you're investing very little or nothing into it. And once we saw that, we realized that, well, we shouldn't approximate the entire process new using a neural SDE. We should just try to learn the difference between the drift of that process of the tradable asset so the difference between that and the process new. Yeah, so just the difference between the red and the blue, basically, right? This should be much more stable. And if you do that, if you look at the difference, this is it. It is on a much smaller scale. This is much easier to learn because you have to learn it on a smaller domain. And that's probably one of the biggest improvements that we got when we're doing the numerics. And this led to considerable improvements in terms of stability, accuracy, everything. Yeah, just a minor change in the parameterization led to pretty good results. Right. But everything is still low dimensional. And I told you I want to go in high dimensions. So Black-Scholes 503. 503 risky assets. We actually calibrated the parameters to market data, and we looked at slightly different constraints, which I feel are more realistic from in terms of application. This is something that I would write down. So we have two conditions. One is that the maximum norm on your portfolio should be less than 0.1, sorry, which means that you're investing not more than 10% of your wealth in any of the assets that you have available. And then we have this L1 norm constraint here, which tells you that the sum of the absolute values of your fractions should be less than 1. This guarantees that, well, you invest in less assets, essentially. While you have 503 available, and if you wouldn't impose any constraints, you would have very small investments in a lot of the assets. Yeah, some slightly long, some slightly short, that just cancel out. You would still be able to satisfy this maximum of 10% constraint. And that's nothing that you want in practice. You don't want to invest in 503 assets because in practice you have to pay transaction costs, you have to do a lot of rebalancing. So you want to restrict the number of assets that you're investing in. And by just imposing this constraint here, you don't have this offset of small short positions, small long positions. And this picks the best assets basically and throws away sets all the non-important ones to zero. At least that's what we were hoping, and what we want to see if this really happens. Here, neural SDE and DBSDE didn't work that well anymore. So that's when we started looking into other things, and we tried PINN for the dual problem, direct optimization for the primal problem. And the result was even better than in the two-dimensional Black-Scholes setting. So 0.176% lost on the initial wealth. I won't go through the pictures except for this one. So what we hoped to see in the constraint actually happened. So you basically pick the best assets, and you go either long or short in those, and you put a lot of assets which don't contribute much, which are not so important, you just put to zero. Yeah, so this type of constraint really allows you to reduce the dimension of the problem. That might be, so I mentioned this because it might be that the performance of the numerics is so good because the constraint forces it to look for a low dimensional structure, get a low dimensional approximation. That's why it still works in high dimension. Still something.
But what do you mean? You're looking for, you're enforcing the sparsity?
Yeah, that's what we're kind of doing with the constraint. So it might be easier to learn a good policy than if you are allowed to invest in everything. Yeah, so if you impose a different constraint,
what did you do then? You penalized with some L1, or what did you do to?
Yeah, we have this
enforce
L1
the sparsity.
Constraint. Yeah, that's the L1 constraint.
That's why.
And if we were to remove this, this L1 constraint, I suspect, we haven't tried it yet, that the results would get worse because it's harder to learn. That's something we just, we still have to evaluate. Yeah. In general, the effect of the constraint on the performance of these kind of methods. Yeah, but this year, I expect that this is really useful.
I missed that at the beginning. Now that you mentioned, yes, you're enforcing. Okay.
Yeah. So L1 constraint is a sparsity constraint. This one is a diversification constraint, if you will. Yeah, so that you're not investing everything in one asset. Yeah. Okay, I won't go through the pictures here for brevity. Instead, let me show you the toughest one that we've tried yet. So that's really 503 dimensional Heston. So 503 risky assets, 503 stochastic volatilities, all of them allowed to be correlated. Yeah. So after the completion of the market, this is 1006 dimensional parameters. inspired by the S&P 500. Yeah, you don't want to, or we didn't want to calibrate a market model, a Heston model to in a 500 and 3-dimensional setting. We just basically took the Black-Scholes numbers and then made some adjustments for the other parameters. So that is decently realistic. Yeah, but we didn't have to, so that we don't have to calibrate the model to actual data. Same constraint as before, except that you're not allowed to invest in the volatilities. Yeah, otherwise, sparsity constraint, diversification constraint. And again, PINN and direct optimization for dual and primal problem, respectively. And here we still get relative difference of 2.67%. I should say that there is still room for improvement. We only ran this once. Yeah, I just got the numbers on last week from Alex. He ran it once. We still have to do some fine tuning, but it's still in my opinion, a very good range. Yeah, so you're wasting less than 3 cents per dollar if you're using the strategy that you get out of this. And here, this is something that we didn't get to work using the neural SDE and the DBSDE approach. This only worked with PINN and direct optimization. So here you start to see differences significantly in terms of numerics. You can have a look at the error that you get in the physics-informed neural network. So dark colors mean it learned really well. This is for basically all large values of the deflator. For very small ones, you get some errors. But the actual process never or rarely runs into the area where the errors are large, so didn't contribute much. So that's good. You can plot a sample path of the auxiliary market variables. And here again, you see that for the volatilities on the bottom, you have these large excursions still showing up. So very similar plots as in the one-dimensional Heston case. And very, very similar structure. Right. Well, I should conclude. So what you just saw in the last hour is that what we want to do is constrain portfolio optimization, high dimensions, numerics, and see how well they are doing. And the beauty is the duality theory, which gives us lower and upper bounds, which we can evaluate numerically, and we don't have to care about theory showing convergence of the individual methods that we use. We can use all kinds of dirty tricks and still are able to get a good estimate on performance. We compared different deep learning approaches to both lower and upper bound and managed to get even accurate results in a very high dimensional Heston setting. And for now, we can say from what we've learned that physics-informed neural networks works pretty well on the dual side. Direct optimization works pretty well on the primal side. I expect that physics-informed neural networks also work well on the primal side. This is something that we will certainly check in the future. It's still work in progress, right? So that's one of the things that is still left to do. The other thing is that I mentioned this earlier. We still don't understand perfectly what the effect of the constraints is. I have the feeling that if you're writing down other constraints, then you lose efficiency, you might lose accuracy. So it probably depends a lot on the kind of constraint that you're imposing, how well these methods work. And the last thing that we would like to do is consider other types of markets with different structure. So here we went for a large number of assets, but there are other ways to increase dimension. For example, if you look at something like a rough Heston, so there's a fractional process for the fractional volatility model, rough volatility model that you could think of as an infinite dimensional Markovian process. And that's where you get the large number of dimensions from, approximating the infinite dimensional, or think of the volatility as an infinite dimensional Markov process and see how well these do and how much you need to get a good approximation for these kinds of problems. And this is structurally a bit different to Black-Scholes and Heston. So we now have a tool available to evaluate how well these go. So that's what we are, that we will certainly do before submitting and writing this up anywhere. Thank you, and apologies
Thank you
for
very
taking
much.
so long.
Very nice talk.
Thank you for this very nice talk. Do we have any other questions from